Hello everyone, welcome back to the class. Today we will continue the topic in asphalt technology. In this lecture, we will focus on the introduction about SUPERPAVE mix design. First of all, we have to know what a SUPERPAVE is. The SUPERPAVE technology was developed by SHRP, the Strategic Highway Research Program, which was established by US Congress in 1987. It's a 5-year program with $150 million research support. The goal of the program was improving the performance and durability of roads. In the program, a research fund of $50 million was spent on developing the performance-based asphalt specification, which can directly relate the lab analysis with the field performance. The SUPERPAVE is actually one kind of products from the SHRP asphalt research. It stands for Superior Performing Asphalt Pavement. This technology actually defines a new standard for aggregates and bituminous binders used in paving as well as mix design changes. In the SUPERPAVE technology, there are some asphalt binder tests which are applied to measure the physical properties that can be directly related to the field performance through engineering principles. Also, these tests are conducted at in-service pavement temperature. Moreover, we will have the SUPERPAVE gyratory compactor to prepare the hot mix asphalt specimen. This is also the third experiment that we will conduct in this class. In order to conduct a high-quality HMA specimen, we need to understand the behaviors of asphalt binders under different conditions. The first one, we want to investigate the impact of temperature, which is the temperature susceptibility. Usually the asphalt is stiffer at low temperature and softer at high temperature. The second behavior is the viscoelasticity. Usually asphalt will act as a viscous fluid at high temperature, especially when the temperature is higher than 100 degrees, and it acts as an elastic solid when the temperature is below zero. The last behavior is aging behavior. In reality, the oxidation of the asphalt will cause age hardening, which will increase the brittleness of the asphalt aggregates. In road pavement design, the asphalt aggregates is commonly applied. In that sense, we also need to understand the aggregate behaviors. In general, there are 3 types of aggregates: natural aggregate, processed and synthetic aggregate, and recycled aggregate. The aggregates in the pavement were usually applied to provide enough shear strength to resist the repeated load applied to the surface of the road. And this kind of shear strength will depend on the internal friction provided by the aggregates. This means the cubical rough and textured aggregates will be preferred as they can offer more resistance to the repeated load, while the round aggregates such as natural signs will not be preferred because they cannot provide enough shear strength. In the pavement design, by mixing the asphalt binder and aggregates, we can get an asphalt mixture, which is usually applied as the asphalt layers in the pavement structure. Also, considering the behaviors of asphalt binder and aggregates, we can summarize the pavement distress caused by the asphalt mixture, including permanent deformation, which is also called rotting, fatigue cracking, and low temperature cracking. As the asphalt mixture can cause various pavement distress, we have to carefully select the procedure for HMA mix design. In summary, the objective of the HMA mix design is developing an economical blend of aggregates and asphalt binder that can meet the design and the functional requirements of road pavements. Traditionally, there are 2 design methods, Marshall and HVEEM methods. The SUPERPAVE technology is the new method to conduct the HMA mixture. The Marshall mix design method was developed by Bruce Marshall in 1939. In this method, it defines certain criteria for the selection of the asphalt binder contents within a suitable density, which will satisfy the minimum stability and range of flow values. With this method, the density and void property of asphalt mixture can be easily measured. Also, the equipment to conduct the design is not expensive and is portable. In that sense, we can easily conduct the field experiment with the equipment. However, in the method, the impact compaction does not simulate the mixture densification in real pavement so that it cannot reflect the real pavement condition. Also, the material stability does not estimate the shear strength of HMA. The second one, HVEEM mixed design method, was proposed by Francis HVEEM in 1920s. In this method, it defines the detailed steps to conduct the aggregate selection, asphalt binder selection, and optimal asphalt binder content determination. The advantage of this method is like we can use the method to determine the mixed resistance to swell in presence of water, and also it has a needing laboratory compaction to simulate the densification of the real pavement. Finally, the HVEEM stability is directly applied to measure the internal friction component of shear strength. Also, there are some disadvantages of this method. First of all, the testing equipment of this method is very expensive and is not portable. In that sense, we cannot conduct any field experiment. In addition, the selections about the binder contents in the method is too subjective, so it relies on the experience of the designer. In order to overcome the disadvantages of the traditional methods, the SUPERPAVE mixed design method was developed. This method identified individual steps which will be applied for the selection of asphalt and aggregate materials. The method also considers the impact of the project's climate and design traffic load for the asphalt mixture, and use this information to integrate the material selection and mix design in the SUPERPAVE mix design. Moreover, the laboratory compaction of the asphalt mixture is accomplished using the SUPERPAVE gyratory compactor (SGC), which is applied to design a mixture that do not exhibit classic tender mixture behavior and do not densify to dangerously low air void contents and different traffic conditions. Finally, the method designs several performance-based tests and models so that we can satisfy the performance requirements of the asphalt mixture for real pavement system. In the SUPERPAVE mix design, there are some performance requirements about the asphalt mixture. First, the mixture should have sufficient asphalt binder so that the pavement can last for longer time. Second, it should have sufficient stability and repeated traffic load so that it is able to provide a reliable service to the vehicles on the road. Third, the asphalt mixture should also have appropriate amount of air voids. Actually, it should have upper and lower limits about the air voids. The upper limit is applied to prevent excessive environmental damage to the pavement, while the lower limit is applied to allow room for the initial densification due to the traffic. Finally, the asphalt mixture should have sufficient workability to reduce the effort in the construction and maintenance. Now let's see how we can conduct the SUPERPAVE mix design to get an appropriate asphalt mixture. Basically, there are 4 steps: material selection, design aggregate structure, design binder content, and moisture sensitivity. In the rest of this lecture, we will go through more details about each step. In the first step, material selection, there are 2 components. The first component is choosing correct asphalt binder. In reality, the asphalt binder is graded to cover almost all the conditions in the road pavement, including project climate and traffic conditions. Usually, the cost of the asphalt binder is one of the most important factors we have to consider in the selection. The second component is choosing aggregates that meet the quality requirement for the mix. In general, the choice of the aggregates is limited to locally available materials so that we can reduce the cost of the pavement. In order to select the correct asphalt binder, we have to understand the properties of the binder under different conditions. In this page, I list several equipments applied for the binder test. The rolling thin film oven RTFO and the pressure aging vessel are applied to simulate the binder aging characteristics. The dynamic shear rheometer (DSR) is applied to measure the binder property at higher and intermediate temperatures. The rotational viscometer RV is applied to measure the binder property at a high temperature, while the bending beam barometer BBR is applied to measure the binder property at low temperatures. The figure here summarizes the capabilities of the equipment on investigating the asphalt binder behaviors and properties and identifying the potential pavement distresses during the test. The selection of asphalt binder actually relies on the performance grade, which is defined by SHRP. In this page, we have one example about the binder grade, PG64-22. Here, PG represents performance grade. The first number, 64, is the average 7-day maximum pavement temperature in Celsius, and the second number, -22, is the minimum pavement temperature in Celsius. Now let's see how we can select the asphalt binder with the performance grade. The table here summarizes the performance grade and the various tests applied for the asphalt binder selection. In the first row, we shows the performance grade. The first column in this row is PG52, and the second one is PG58, and it also has some sub-columns with a -10, -16, -22, and the interval is 6 degrees. In the first column, it indicates that the average 7-day maximum pavement design temperature should be less than 52 degrees, and for the second column, that means it's less than 58 degrees. While for the sub-columns, if we have -10, it indicates that the minimum pavement design temperature should be higher than -10. Similarly, will be applied for the other sub-columns. Also, with respect to the binder tests, we have to set up the constant temperature for the test with the dynamic shear barometer. For example, for the PG52, the temperature is always set as 52 degrees. The binder test with dynamic shear barometer is actually applied to identify the specification requirement to addressing rotting in the road pavement. We actually apply two different loads, 1 kilopascal and 2.2 kilopascal, to address rotting. If the load is increased to 5,000 kilopascal, then we can use the information to address the fatigue cracking. Moreover, for the test with respect to creep stiffness and direct tension, then we can use the information to identify the requirements to address the low temperature cracking. In the selection of asphalt binder, we not only need to determine the temperatures applied for the performance grade, but also need to specify the reliability. In general, the reliability is defined as the percent probability in a single year that the actual temperature will not exceed the design temperature. And with a higher reliability means that the selection of the asphalt binder will be more reliable, and there will be lower risk for the material to fail. Now let's see how we can define the reliability for the asphalt binder in the performance grade. The figure on the top shows the reliabilities under 7-day maximum air temperature. Here we can find that the 50% reliability is 32 degrees. It indicates that the probability that the temperature less than 32 degrees is 50%. While similarly for 98% reliability, the value is 36. It means that the probability with the temperature less than 36 degrees is 98%. So that's the definition for the 7-day maximum air temperature, while the definition for the minimum temperature will be a little bit different. Actually, we need to consider the probability in the opposite direction. Let's go to see the figure at the bottom. Here, if we consider the 50% reliability, the value should be minus 21 degree. It will represent the probability with the temperature higher than minus 21 degree, and the probability is 50%. Similarly, for 98% reliability, we will find the minimum temperature should be higher than minus 29 degree, and the probability is 98%. So that's the way for us to identify the reliability for the performance grade. Now let's check one example to see how we can select performance grade with reliability. In this figure, we have the distributions of the 7-day maximum temperature, which is the red curve here, and the minimum temperature, that will be the blue curve here. We want to find out the most appropriate performance grade for 50% reliability and 98% reliability. So first of all, we have to identify the 50% and the 98% reliabilities. For 7-day maximum temperature, we can find out the 50% reliability as 55 degree. For 98%, that is around 62 degree. And for the minimum temperature, the 50% reliability is around minus 24, and for the 98% reliability, it's around minus 32. Also, we know that for the binder grade, it's usually defined with the 6-degree increment. So we have the maximum 7-day temperature varies from 52 degree, 58 degree, 64 degree, and so on. While for the minimum temperature, we have the value around minus 22 degree, minus 28 degree, minus 34 degree, and so on. And then with this information, we can identify the 50% reliability for the performance grade. First, for the 7-day maximum temperature, we find that for 50% reliability, it's 55 degree. So we have to select a temperature which is a little bit higher than 55. So the closest one would be 58. So we will choose PG 58. And then for the minimum temperature, we need to find out the one which is a little bit smaller than the 50% reliability, that is minus 24. So the closest one is minus 28. Then the performance grade we will choose is 58 minus 28. Similarly, we can find out the performance grade for 98% reliability. So for the 7-day maximum temperature, the closest one is 64, and for the minimum temperature it's minus 34. What we get is PG 64 minus 34. So that's the way for us to choose the performance grade for the asphalt binder. The table here shows the performance grades applied for different asphalt binder with various temperatures and the results from different binder tests. It will cover most of the situations on the roads. In addition to the temperature observed in the field and the binder tests conducted in the lab, we also need to consider the impact of the traffic to the selection of the binder performance grade. For example, if we consider 3 roads in the same location, we will usually put the performance grade 64 minus 22 for tall roads with the speed around 90 km per hour. But for the tall booths with slow traffic, we will take the performance grade 70 minus 22. For the weigh station where all the trucks are stopped, then we have to take the performance grade 76 minus 22. The difference about the performance grade selection is actually caused by the traffic on the road. The table here shows how we can adjust the performance grade based on the traffic conditions. Here we are considering two factors. The first one, which is shown in the first column, would be the designed traffic load. It's measured in 20 years with ESAL, which would be the equivalent standard actual load. So it will increase from low value to high value. And the second factor is the speed of the traffic. We categorize the speed into three types. The standing speed, which is less than 20 km per hour, slow, which is 20 to 70 km per hour, and standard, which is higher than 70 km per hour. For the first row with a very low traffic load, less than 0.3 million in 20 years, then we don't need to do any adjustment. While for the other traffic load, if we are considering the standing traffic, which means the speed is less than 20 km per hour, then we have to apply two increments, which would be 2 times 6, that is 12 degrees, for the 7-day maximum speed temperature. If it's only with the slow traffic, then we just need to apply one increase, that is 6 degrees to the 7-day maximum temperature. In addition, for the standard traffic, usually we don't need to do any adjustment. But when the load is very high, which is larger than 30 million, then we have to apply one increase, that is a 6 degree increase for the 7-day maximum temperature. So that's the way for you to do the adjustment about the performance grade for the asphalt binder based on the traffic load and the speed of the traffic. Now let's check the second component of material selection, which is choosing the appropriate aggregates to meet the quality requirements of the mix. The page here lists a set of the characters for the HMA aggregates, including maximum size and gradation, cleanliness, toughness, particle shape, surface texture, absorptive capacity, affinity for asphalt cement, and frictional property. In general, there are 5 types of aggregates applied for asphalt mixture. Number 1, stone, 12.5 mm chip, 9.5 mm chip, manufactured sand, and screen sand. The first 3 are the coarse aggregates, and the last 2 are the fine aggregates. The selection of aggregates is determined by their own properties. In the SUPERPAVE mix design, we will consider 4 different aggregate properties, including coarse aggregate angularity, fine aggregate angularity, flat or elongated particles, and clay content. The coarse aggregate angularity (CAA) is very important to ensure appropriate aggregate interlocking and prevent excessive HMA deformation under repeated traffic load, which means it's able to prevent the potential rutting to the road pavement. The test for CAA is defined by AASHTO TP61. In the test, the CAA is estimated by visually inspecting a small sample of coarse aggregates and separating the sample into those pieces with a fractured face and those without. And if more than one fractured face is inspected, the same procedure will be applied to identify the portion with 2 or more fractured faces. With this test, we are able to identify the percentage of fracture in coarse aggregate. The CAA can also be estimated with another test, AASHTO TP56, the uncompacted void contents of coarse aggregate. With this test, we are able to identify the void content. in the coarse aggregate, and with a higher void contents, CAA will be larger. The table here summarizes the typical CA values for some coarse aggregates. For number 1 stone, the percentage of 1+ fractured face is 92%, and in the test, the percentage for 2+ fractured faces is around 88%. For 12.5 mm chip, there are some minimum percentage requirements. For 1+ fractured face, the minimum percentage is 95. For 2+ is 90%. In the test, we get a 97 for 1+ fractured face, which is higher than the minimum value, and for 2+ is 94%, which is also higher than minimum value. In addition, for 9.5 mm chip, we will usually conduct the test for 1+ fractured face. The minimum percentage should be 95%, and in the test we found it's 99%, which means that the aggregate is appropriate for the SUPERPAVE mix design. The second property is the fine aggregate angularity FAA. The FAA is usually defined as the percentage of air voids presenting the loosely compacted aggregates, with the grain size smaller than 2.36 mm. The FAA value is very important to ensure a high degree of internal friction and rotting resistance for the road pavement. Usually the test of the FAA is defined by AASHTO T304. In this test, we will estimate the FAA by measuring the loose uncompacted void contents of fine aggregate samples, and the test results are influenced by particle size, surface texture, and the grading of the aggregates. The figures here shows the equipment applied for the uncompacted voids test. With this test, we are able to estimate the uncompacted voids of the aggregates, and the value is estimated through the equation here. In this equation, V is the volume of the cylinder, and W is the sample mass, and GSB is the dry bulk specific gravity. You can find out more definitions about the bulk specific gravity in the tutorial 3. The table here summarizes the typical void contents for some fine aggregates. For manufactured sand, the minimum void content should be 45%, and the typical value is around 52%. For the screen sand, there isn't any minimum requirement. The typical value is usually around 40%. The third aggregate property is the flat or elongated particles. Actually, the presence of this kind of particles will increase the difficulty of compaction for the aggregates. In addition, these particles also have a tendency to fracture during the compaction, which will make the aggregate finer, and they are possibly cause lower than expected VMA. The test for flat and elongated particles is used to determine the dimensional ratio for aggregate particles of specific sieve size. The test is actually developed by ASTM D4791. The figure here demonstrates the instruments applied for this test. The test for flat or elongated particles is only applied for coarse aggregates. The table here summarizes the typical percentage of flat and elongated particles for the 3 different coarse aggregates, and the values are all 0%. Also, for 12.5 mm chips, we want to make sure that the percentage is less than 10% to satisfy the requirements of the SUPERPAVE mix design. The last property, clay content, is usually measured in the sand equivalent test. We have already introduced the procedure of this test in our previous lectures. Basically, we need to find out the clay rating and sand rating in the experiment, and the ratio between the sand rating and clay rating is defined as the sand equivalent. With a higher sand equivalent, the clay content will be smaller. The table here summarizes the typical sand equivalent values for two fine aggregates. For manufactured sand, the sand equivalent should be higher than 45, and in the test we found out the typical value is 47. For this green sand, we don't have any minimum requirement, and the typical value is 70. With the defined aggregate properties, we can then summarize their requirements for the SUPERPAVE mix design with the consideration of different traffic loads. The table here summarizes the requirements. The first column shows the design traffic load, which is measured with ESAL, equivalent standard axial load in millions. In this table, we also have the conditions about the pavement structure. Less than or equal to 100 mm indicates that less than 25% of the layer with the applied aggregates is within 100 mm of the surface, and higher than 100 mm will be the other case. Now we can see how we can read this table. For example, if we are considering the case with the traffic load between 10 and 30, and we also assume that less than 25% of the layer is within 100 mm of the surface, which would be the case of less than or equal to 100 mm. With that, we have to read 4 values in this table. First, for the coarse aggregate angularity, there are 2 minimum requirements. For the CAA, with respect of 1 plus fractured face, the percentage should be higher than 95%. For 2 plus, it should be higher than 90%. And for the fine aggregates, the uncompacted void content should be higher than 45%. Also, for the sand equivalent, the percentage should be higher than 45%. In addition, for the flat and elongated particles, the percentage should be always smaller than 10%. So that's the way for us to get all the requirements for one specific traffic load in the SUPERPAVE mix design. So that's all about the lecture today. Thank you very much for your attention. In the next lecture, we will continue the introduction about the rest 3 steps in the SUPERPAVE mix design.